Okay, so now let's extend our understanding of the measurement principle to doing a measurement in an arbitrary basis. So let's go back and review what we had. So again, we are thinking about a two-level system, which is the state of an electron of bounded energy. So it's either in this ground state or excited state, represented by 0 and 1. So in general, the state of the system psi is some superposition alpha 0 0 plus alpha 1 1. And we already saw that we can view this as a vector in a two-dimensional vector space. It's a complex vector space, but for convenience in drawing it, I'll pretend it's all real. So this is 0 and 1, and now a state psi is just some vector like this. Okay. And we also saw what it meant to do a measurement. So when we do a measurement, the state collapses into either the 0 state or the 1 state. We either see the ground state or the excited state with probability cosine squared theta, where theta is the angle that psi makes with the 0 state. Okay? And the new state is either the ground state or the excited state. But now, in general, what we can do is we can measure not just to see whether the state is a ground state or excited state. We can pick any orthogonal basis for this space. So, in other words, what we can do is we can pick some basis consisting of the state U and U perp, and we can do a measurement in this arbitrary basis U perp. And then the rules of the game are going to be completely analogous. So the outcome is going to be U with probability, let's call this angle theta prime. So the outcome will be U with probability cosine squared theta prime, and U perp with probability sine squared theta prime. And of course, the result of the measurement is that if the outcome is U, then the new state is in fact this state U. And in the other case, the outcome is the new state is really U perp. So here's another way of saying this whole thing. So let's say that U was beta 0 0 plus beta 1 1. So U perp might be minus beta 1 0 plus beta 0 1. So these are orthogonal states. And now the probability you have this outcome cosine squared theta prime. This is exactly the inner product between the state psi and U whole squared. So if we were to write the inner product this way, it's the inner product of U and psi squared. And this is the inner product between U perp and psi squared. Okay, so let's see some examples and let's see how to work with all this. So let's first talk about a very special basis called the Hadamard basis. This is a very important basis. It consists of these two states, the plus state, which is this superposition of 0 and 1 with equal magnitudes, 1 over square root 2 0 plus 1 over square root 2 1, and the minus state, which is 1 over square root 2 0 minus 1 over square root 2 1. So what distinguishes these two states is the sign, the phase here in front of the 1. So now you could ask, can we distinguish this plus state from the minus state through a measurement? Well, so let's do a measurement in the 0 1 basis, in the standard basis. So if we do a measurement in the standard basis, we end up seeing, and if we start with the state plus, then you see 0 with probability 1/2 and 1 with probability 1/2. In this case, the new state is 0. In this case, the new state is 1. What about if we start with the minus state? Well, once again, we see 0 with probability square of this, which is 1/2, and 1 with probability square of this. So the phase goes away with probability 1/2. And again, in each of these cases, the new state is 0, 1. So the results are completely identical when we do a measurement. And the reason is clear. It's because the probability is determined by the square of the amplitude. And so whether it's positive or negative, it makes no difference to the outcome. So is there any way we can actually distinguish the plus state from the minus state? Well, so here's an idea. Why not measure in a different basis? So measure in a different basis, in some u-perp basis. But which basis would you pick? Well, it's clear, right? If you want to distinguish plus from minus, why not measure it in the plus minus basis? That's a perfectly good basis. And so if you measure in the plus minus basis and you start with the plus state, what do you see? Well, the outcome is plus with probability 1, minus with probability 0. Right? And in this case, the new state is plus. Well, this never happens, but if it were to happen, the new state would be minus. If you start with the minus state, you see plus with probability, well, 0, and minus with probability 1. So you end up distinguishing these two completely with probability 1. You know for sure if you measure in the plus minus basis and you start with the plus state, you always get plus. And if you start with the minus state, you always get outcome minus. Okay, but now suppose we start from a general state, psi, and you want to measure it in the plus minus basis. How do you figure out what's the probability you see plus and what's the probability you see minus? So this is an exercise in linear algebra, and we are going to go through it just to make sure that you remember your linear algebra. And also, when we go through it, we are actually going to be doing this in this ket notation. So it'll not only be a review of linear algebra for you, but it'll also be a way to familiarize yourself with this ket notation. Okay, so here's our picture. This is the standard basis, the 0, 1 basis. Here's the plus minus basis. They make a pi by 4 angle. Okay, here's plus in terms of 0 and 1 and so on. And now what we want to do is we are given some state psi. Let's say it happens to be, it happens to be a state psi which makes a 60-degree angle. So this is what psi looks like. It's 1/2 0 plus square root 3 over 2 1. And now we want to measure the state in the plus minus basis. So how do we figure out what's the probability of seeing the outcome plus? Okay, so one way to compute it is just by computing inner products. Right? Remember, the probability that we see plus is the square of the inner product, or that psi makes with plus. So we write it out. Psi is this state, plus is that state, and we take the inner product, take the square of the magnitude. So when you take inner products, you get 1/2 times 1 over square root 2 plus square root 3 over 2 times 1 over square root 2. And so you add that, take the square, and you get some number. Similarly, you can carry out this process also for probability of minus. It's the inner product that psi makes with the minus state squared. But you can also, you can work it out exactly like this, or you can also say that this is 1 minus the probability of plus, which is just 4 minus 2 square root 3 over 8. Okay, so that's one way of computing these probabilities. Here's another way we can do this. So what we can do is we can do a change of basis. So to figure out what the state psi, what's the probability of seeing plus or minus when we measure psi in the plus minus basis, what we'll do is first we'll rewrite psi in the plus minus basis. So we want to express it as beta naught plus plus beta 1 minus. And then if we are doing the measurement in the plus minus basis, we can just read it off. The probability of plus is beta naught magnitude squared, and probability of minus is beta 1 magnitude squared. Okay, so how do we do this change of basis? Well, so what we want to do is we want to rewrite the 0 state in terms of plus and minus, and the 1 state in terms of plus and minus. So you can do that either by inspection, by seeing that 0 must be equal superposition of plus and minus, or you can just solve, right? If you add these two together, you'll get that plus plus minus, well, these two vectors will cancel, is equal to 2 over square root 2 times 0. Or 0 is, well, you just transpose and you get 1 over square root 2 plus 1 over square root 2 minus. And similarly, if you subtract these two, you get square root 2 times 1. And so 1 is 1 over square root 2 times plus minus minus. Okay, so now we just go back and substitute this in here. So psi, which is this superposition, we just substitute for 0 as being 1 over square root 2 plus 1 over square root 2 minus, and similarly for 1. And then we simplify, so we gather the pluses together, the minuses together. And so this is beta naught, that's beta 1. And now the probability that we see a plus is the outcome of the measurement is plus, is just beta naught squared, magnitude squared, which again gives us the same value as before.